You have learnt that there are two performance parameters in the cruise, range and endurance. Let us now consider range. Range is a more useful performance parameter than endurance, and one that aircraft designers continually try to improve. Whereas endurance is about airborne time, range is more concerned with distance covered, and it is, therefore, sometimes referred to as fuel mileage. Maximum range can be defined as being the maximum distance an aeroplane can fly for a given fuel quantity consumed, or to put it another way, the minimum fuel used by an aeroplane over a given distance. This latter expression of range is more commonly used for commercial operations. As a formula, range is simply the distance in nautical miles divided by fuel quantity in kilograms. However, in the same way as we did for the formula for endurance, we must adjust our range formula needs in order for it to give us useful information. The top line of the formula is air nautical miles per hour, and the bottom line of the formula is kilograms of fuel per hour. Thus, the formula now reads true airspeed divided by fuel flow. This is the formula for specific air range. The formula shows that specific air range is defined as the ratio of true airspeed over the fuel flow. You may recall from the endurance lesson that fuel flow is specific fuel consumption multiplied by drag for a jet, and specific fuel consumption multiplied by power required for a propeller-driven aeroplane. Looking at the formulae, it is now obvious that in order to maximize the specific range of the aeroplane, true airspeed must be high and the fuel flow must be low. Let us now focus on the specific air range of the jet aeroplane. We stated earlier that to maximize the range, the TAS must be high and the specific fuel consumption and the drag must be low. Shown on screen is the drag curve for a jet aeroplane. If the aeroplane were to fly at VMD, then of course the drag force would be at its lowest. Referring to the formula, it seems we have solved one of the points, namely how to make drag as low as possible. However, looking at the graph, notice that because the drag curve is fairly flat at the bottom, the speed may be increased significantly from VMD for only a small drag penalty. From the formula, we can therefore see that whilst drag has increased a little, which is bad for range, the airspeed has increased significantly, which is good for range. Consequently, the overall effect is that there is an increase in specific range. The speed at which the speed-drag ratio is maximized may be read from the graph at the tangent to the curve. You may recall that this speed was 1.32 VMD. Therefore, it is 1.32 VMD that is the speed for maximum range for a jet aeroplane. There is now only one remaining item left in the formula which still needs to be resolved. In order to increase range even more, specific fuel consumption must be decreased. You may recall that the only way to do this for a jet aeroplane is to operate at as high an altitude as possible. Operating as high as possible will give us a higher true airspeed for any given indicated airspeed, which again will improve the specific range. Having completed the analysis of range for a jet aeroplane, let us now examine specific air range for a propeller aeroplane. We stated earlier that to maximize the specific range, the TAS must be high, and the specific fuel consumption and the power required must be low. Shown on screen is the power required curve for a propeller aeroplane. If the aeroplane were to fly at VMP, then of course its engine would be delivering minimum power required for level flight. Referring to the formula, it seems then that we have solved one of the components, namely to make power required as small as possible. However, at the graph, notice that because the power required curve is fairly flat at the bottom, the aeroplane speed may be increased significantly from VMP for only a small penalty increase in the power required. From the formula, we see that whilst power required has increased a little, which is bad for range, the airspeed has increased significantly, which is good for range. Consequently, the overall effect is an increase in the range. The point at which the speed-power ratio is at a maximum is the tangent point of the curve. You may recall that this speed is VMD. Therefore, it is VMD that is the speed for maximum range for a propeller aeroplane. There is now only one remaining item left in the formula which still needs to be resolved. In order to maximize range even more, specific fuel consumption must be decreased. However, you may remember that specific fuel consumption for piston aeroplanes is fixed, whereas for turbopropeller aeroplanes which use jet engines, the specific fuel consumption decreases with altitude. Having studied how to achieve maximum range for both jet and propeller engines, let us now examine what factors affect range. The first of the factors to discuss is the effect of weight. You will recall that increasing the weight of the aeroplane increases induced drag, and thus moves the total drag curve and power required curve up and right. Looking at the jet diagram which uses drag, you can see for higher weights the aeroplane is subject to a higher drag force and therefore requires a higher rate of fuel flow. This will decrease specific range. However, notice that the speed for maximum range, 1.32 VMD, is now higher. For a propeller-driven aeroplane, it is much the same. At higher weights, more power is required. Therefore, fuel flow increases and range decreases. However, notice too that the speed for best range, VMD, is higher. Remember also that at higher weights, the operating altitudes are reduced, which for a jet aeroplane means that the specific fuel consumption increases, because at lower altitudes, the jet engine is less efficient. One of the most important issues that airline operators need to consider is the choice of the aeroplane they operate. This choice is mainly based upon the required aeroplane's payload and range. These requirements can be best described by going through a typical example. Shown on screen is the payload range graph for a Boeing 777. On the vertical axis is the payload in thousands of kilograms, and the horizontal axis shows the aeroplane range in thousands of nautical miles. On the right-hand side of the graph is a bar chart symbolizing aeroplane mass. Here, the aeroplane is at its dry operating mass, DOM, which essentially means the mass of the aeroplane without fuel or payload. This is shown on the bar chart and by the flashing blue marker on the bottom left-hand side of the graph. As the payload is added, notice that the blue mark moves up the payload axis. Notice too that the total mass of the aeroplane is increasing as shown by the bar chart. However, payload will reach a maximum when either there is no more space on the aeroplane or the aeroplane has reached its zero fuel mass, ZFM. Notice that the range at this point is 0 because no fuel has been added yet. This point is marked as A. Fuel is now added to the aeroplane and the marker point moves to the right, showing an increase in range. Adding fuel can continue until the maximum structural takeoff mass is achieved. This is shown by point B on the graph. Notice that the weight bar on the right is now at the top. Although maximum mass has been reached, it is unlikely that the tanks are full at this stage. To increase range further, more fuel must be added. But since the maximum mass has been achieved, the only way to add more fuel is if some of the payload is exchanged for fuel. Now the marker will start to move down and right. This shows that range is increasing, but the payload is decreasing. Swapping payload for fuel in this way can only continue until the tanks are full, as shown by point C. The only way to increase the range beyond this point, even though the tanks are full, is to remove the rest of the payload. At point D, the aeroplane has full tanks, maximum range, but no payload. In the majority of airlines, the trade-off between range and payload is carried out on initial aeroplane purchase and thereafter during in-flight planning. As a pilot, it is unlikely you will be required to work through these graphs other than to check and confirm the data that has been prepared in advance for you. Another factor affecting the range is the aeroplane's configuration. You will recall that deploying the flaps and undercarriage increases parasite drag and thus moves the total drag curve and power required curve up and left. Looking at the graph for the jet airplane and using the drag curve, you can see that with the gear and flaps deployed, the aeroplane has more drag and therefore needs more thrust, and which, in turn, requires greater fuel flow. This will decrease the range. However, notice that the speed for maximum range, 1.32 VMD, is now lower. Looking at the graph for a propeller aeroplane, you can see that matters are much the same. With gear and flaps deployed, more power is required. Therefore, fuel flow increases and range decreases. But also notice that the speed for best range, VMD, is lower. A point always to bear in mind in the cruise is that any increase in parasite drag will be detrimental to range and endurance. Increases in parasite drag can be caused by any number of things such as damaged and misaligned surfaces. The extra drag created by misaligned or misrigged airframe surfaces creates a type of drag called excrescence drag. This can be more than 4% of the airplane's total drag. Careful pre-flight inspection should reveal misaligned or misrigged surfaces. An important point to consider over which the pilot has direct control is aeroplane trim. A pilot must periodically check the aileron and rudder trim, the spoiler misfire, and the trailing edges to ensure that the aeroplane is in trim and is in balanced flight. Monitoring the aeroplane's control surfaces will help to reduce the extra drag and extra fuel consumption that out of trim and unbalanced flight can cause. Lastly, contamination on the airframe from airframe icing can affect fuel flow. This icing will not only change the shape of the wing, making it less efficient at producing lift, but it will also increase weight and drag. All this is detrimental to aircraft performance and will reduce the aeroplane's range.